The theme of this year's Mathematics Week is counting. In this lecture we'll explore the concept of counting. We'll first consider what it means to count a finite number of objects as we do in everyday life, and then we'll extend this idea to explore the cardinalities of infinite sets. So let's first consider the concept of counting as we all know it. It's a skill we learn early in life, but it's actually quite profound. And it's understandable that we take it for granted as being an easy thing to do. But we didn't always find it easy. There are mistakes that all children make when they're learning to count. And for me, it's in the consideration of those mistakes that we understand what counting truly is mathematically. So how do we count the number of Lego bricks in this slide? Some of you are probably sat there thinking, well, it's so obvious, I don't even need to go through the process of counting, I can just see that there are 5 Lego bricks. And indeed, our minds are so well versed with quantifying small numbers of objects that we can almost see numbers just by looking at groups of objects all clumped together. If you're thinking slightly more deeply about it, you might say, well, we point at each object in turn, we work our way through the natural numbers, and when we get to that last object, we hit 5, so we conclude that there are 5 Lego bricks. So, is counting just assigning numbers to objects? Well, the answer is yes, but it has to be done in a certain way, and there are many ways that we can get it wrong. So, I could miss an object out, I could assign the same number to different objects, I could miss a number out as I'm making my way through the natural numbers, or I could perhaps count the same object twice. Each of these would result in me miscounting the number of Lego bricks. So what precisely must we do in order to count correctly? So when we assign numbers to objects, what we're actually doing is we're mapping from a set of numbers to a set of objects. So these diagrams here are representing different types of mappings and functions. A mapping is just a rule which sends elements of one set to elements of another. A function is something much more precise. It sends every element in a set, called the domain, and it assigns it uniquely to another element in another set called the codomain. And what we have here are 4 incorrect ways of counting that we've just considered, and a correct way of counting in the bottom right. So, in the top left, this corresponds to counting the same object twice, where 2 numbers have gone to the same object. And this represents a many-to-one function. The function is not many-to-one, it's one-to-one, or injective. The middle one on the left represents missing a number out as we're working our way through the natural numbers. So in some sense we can think of this as not every element of the domain being mapped somewhere. So that's a mapping and not a function. The bottom left is assigning the same number to 2 different objects. So here we haven't mapped every element of the domain uniquely into the codomain, so that's also a mapping and not a function. In the top right, we've missed an object out, so not everything in the codomain is mapped to. The property where everything is mapped to is called surjectivity. Now, in order to count correctly, we have to define a function that's both injective and surjective, and that's called bijection. So what we're doing is we're mapping from a domain into a codomain in a one-to-one fashion, such that everything in the codomain is mapped to. And the way we can think about this is essentially uniquely pairing every element from the domain with something in the codomain. So why are bijective functions important? 2 sets have the same size when there exists a bijective function between them. When we count objects, what we're actually doing is constructing a bijective function between a set of standard size and the set of objects that we're counting. And when we teach children to count, we're actually teaching them that there are these sets of standard size, these are the elements in them, and we teach them how to construct that bijection from those sets of standard size to the set of objects that they're counting. So we're very good at counting finite numbers of objects, but what's much less understood is counting infinitely many objects. And you might ask, well, if there are infinitely many, why would we need to count them? Surely there are just infinitely many. But that question has some surprising answers. So firstly, let's think about where we've encountered infinity before. The two most obvious examples that come to mind are the set of natural numbers and the set of real numbers. So the set of natural numbers are the positive whole numbers, and it's quite easy to accept that they just go on forever, and we don't really worry about it too much, they just go on, and that's that. The other place where we've seen infinitely many numbers is on the real number line. These are not just the positive whole numbers, but any numbers that you can possibly think of, before you start defining the square root of -1 and things like that. So this contains fractions, recurrent decimals, rational numbers, transcendental numbers, etc. This is the x-axis on our beloved graphs. Of course, we only draw a short section of it. It extends infinitely in both directions. So we're aware of sets of infinite size, but there's a fundamental difference between these two infinite sets. The natural numbers, as is begun to be shown here, can be listed, and we could go on listing them. But the real numbers, they cannot be listed. If you think of any real number, there isn't a next real number. There isn't a next number after pi. If you think of any number larger than pi, you could find a number between pi and the one that you just thought of. Namely, you would just halve the difference between them and add it to pi. And it seems that no matter how much we zoom in on the real number line, we just find infinitely many more numbers, and that infinite nature doesn't really stop. So a surprising fact that illustrates this density quite nicely is the fact that there are the same number of numbers between 0 and 1 as there are on the whole real number line. Which is quite remarkable when you first hear it, because if we consider that whole real number line, and then just consider this section here, between 0 and 1, there are the same number of numbers. And that goes against our intuition, because that section there is contained within the real number line. And containment, in our world, when we work mostly with finite things, containment means that it's smaller. So how do we convince ourselves that this is in fact true? So earlier we said that if we can match up every element in one set with every element in another, those sets have the same size. And we do this by forming a bijective function between them. So here we can see a transformation of the tan function, and every element from 0 to 1 is mapped in a one-to-one fashion to every element of the real number line. Just that this time the real number line is on the y-axis, so it's going vertically down. Okay? So if you're convinced that this is a bijective function, which you should be, because it is, then this function is enough to show the result. So what about these two infinite sets, n and r, representing the natural numbers and the real numbers? Can we form a bijection between those two sets? We've just seen that the set from 0 to 1 is the same size as the reals. So if we could form a bijection between the natural numbers and that interval, we could form a bijection from the natural numbers to the reals through composing functions. But a bijection from the natural numbers to that interval doesn't exist, and the following argument shows us why. So if there did exist a bijection between the natural numbers and this interval from 0 to 1, then we could list all of the numbers from 0 to 1. However, when we do this, or when we try to do this, we can always find a number between 0 and 1 that isn't in our list. And we do that by constructing this number here, x. Okay? And we look at our list, and for the nth number, we look at the nth decimal place, and we just make sure that the nth decimal place of this is different. So we just choose a digit that's different than the nth number in our list at the nth decimal place. So this will definitely be a number between 0 and 1, but it's not in our list, and that contradicts our assumption that we could list them all in the first place. That's the contradiction that we're looking for. So there doesn't exist a bijection between the naturals and this interval from 0 to 1. So what this tells us is that the infinite nature of the natural numbers is different to the infinite nature of the real numbers. What's fascinating is that that infinity is actually different, because there's no bijection between the natural numbers and the real numbers. So we have these two sets, they're both infinite in size, but they're not the same size. They're different sizes of infinity. And we refer to the infinity of the natural numbers as countable, and denote it with this symbol here, Rlef naught, and the infinity of the real numbers as uncountable, and denoted by Rlef 1. So Rlef is the first letter of the Hebrew alphabet. So we now have these two different sizes of infinity, and since the naturals can be embedded into the reals, we see that the infinity of the reals is bigger than that of the naturals. But is there anything in between? And this brings us to the continuum hypothesis proposed by Cantor in 1878. It says there is no set of cardinality that sits strictly between that of the cardinality of the natural numbers and the cardinality of the reals. And this baffled mathematicians for decades, until Gödel and Cohen showed that using standard set theory we can't prove or disprove this hypothesis. So firstly, in 1940, Gödel showed that the continuum hypothesis cannot be disproved within the standard axioms of set theory. And later in 1963, Paul Cohen showed that it also cannot be proved within the standard axioms of set theory. So in some sense, the continuum hypothesis is independent of the axioms of set theory. But in short, we have these two infinite sets, they have different cardinality, and we can't prove or disprove the existence of anything sitting strictly in between. So where does this leave the rationals? In terms of sets, it sits strictly between the natural numbers and the real numbers. So every natural number is rational, every rational number is real. But not every real number is rational, not every rational number is natural. And it should be clear that the rational numbers have also infinite cardinality. And since we cannot prove that there is an infinity between that, the naturals and the reals, this really means one of two things. That either the size of the rationals is the same as the naturals or the reals, or that we simply have absolutely no idea about that size of infinity, and we could never prove anything about it either. And that sounds unlikely, as we're about to see. So it turns out that the rationals have the same cardinality as the natural numbers. And we can see this by forming a bijection between the rational numbers and the natural numbers. So in order to prove this, we're going to construct this bijection. And it helps by listing out the rationals in a grid, like this, going infinitely far this way, infinitely far downwards. And you'll notice that some of the elements are highlighted red, because sets are collections of objects listed without repetition. So where a number has already appeared, we would delete those ones. And we're going to try and map this now as a bijection to the natural. So we might try this by working along the top row, setting 1 to 1, 1/2 to 2, 1/3 to 3, 1/4 to 4, and so on. But the problem with that is that that top row is infinitely long, and we'd never make it to the end of it. And that would mean that any rational number that sits strictly beneath that top row would never be mapped anywhere. So instead what we do is we take this path which kind of snakes through the grid. So we start here at 1, we send 1 to 1, 2 to 2, 1/2 to 3, 1/3 to 4, skip over this one because it's already in the set, 3 to 5, 4 to 6, and so on. We keep snaking our way through the grid. So what we see is that the rationals are being mapped into the natural numbers in a one-to-one fashion. But also, for any natural number n, we can find the nth rational number as listed in this way. And that will be the rational number that's mapped to n. So it's also surjective. So this forms a bijection between that set of rational numbers and the natural numbers, and hence those two sets have the same size. So whilst we have this strict inclusion of sets, in terms of cardinality we have this result here where the rationals is the same size as the naturals and the reals is something different. So it turns out that there's a relationship between these sizes of infinity, and to see this we're going to look at something called the power set of the natural numbers. So the power set is the set of all subsets of the natural numbers. So this is clearly an infinite set, because if nothing else it contains all the subsets of size 1, and we know that there are infinitely many of those. So how about this set? Is it the same size as the natural numbers? Same size as the reals? Or perhaps some other size of infinity? So we can show that a power set is uncountable in much the same way that we did the interval from 0 to 1. And it follows the same sort of diagonal argument. So we first suppose that this set is countably infinite, so there's a bijection to the natural numbers, and therefore we can list out the sets, the subsets of the natural numbers. And then we create this other set here that's given by the rule that n is in D if and only if n is not in A sub n. So D is also a subset of the natural numbers, but it differs from everything in our list, at the very least, by the element n. So this contradicts our assumption that we could list them all in the first place. And so the subsets of the natural numbers are not countable, they are uncountably infinite. And it turns out that this set here is the same size as the reals. So there is a bijection between the power set of the natural numbers and the real numbers. If we think about the size of that power set in a different way, that's when we can find the relationship between Rlf0 and Rlf1. So to determine the size of a power set, we need to think about how many subsets we can form from a set. The way we do that is to look at each element in turn and decide whether or not we're going to include it in a subset. So for every element in our set we have two choices: include it in the subset or not. And so with that we have 2 to the power of the cardinality of n subsets of the set of natural numbers, which means that 2 to the power Rlf0 is equal to Rlf1, given that these two have the same cardinality. And you might say, well, you can't take the infinite power of a number. Well, you sort of can. Okay, so this here is representing the size of this set. This here is representing the size of this set. It can be shown that these two things are the same size. So if they're both representing things of the same size, then they must be equal to each other. So We know that we can't prove the existence of an infinite cardinality between these two. Well, what about beyond these two? So I think this guy here, Buzz Lightyear, he gets a bit of a hard time. And people implicitly mock his to infinity and beyond, as if it's obvious that there's nothing beyond infinity. But maybe Buzz Lightyear is well versed in the study of transfinite, cardinal and ordinal arithmetic within axiomatic frameworks, such as the Mallet-Frankel set theory with axiomatries, and he doesn't quite get the credit he deserves. However, it turns out that if we take a power set of the reals, we obtain another set of infinite cardinality, but one that is not equal to Rf0 or Rf1. It's again another larger infinity, labelled really imaginatively Rf2. And one can continue this process and look at the power set of this set and construct yet another larger infinity, and it goes on. And furthermore, there's a generalized continuum hypothesis that states that there's no set of intermediate cardinality in any two of these consecutive RF alphas. So, in fact, just as there are infinitely many possible cardinalities for sets of finite size, there are also infinitely many different cardinalities for sets of infinite size. But hopefully at this stage of the lecture, rather than just accepting that there are infinitely many and just saying, well, that list clearly goes on forever, hopefully you're questioning, if there are infinitely many different sizes of infinity, how large is that infinity? Thank you for listening.